Welcome to the session. So now when I'm talking about a 3D viewing, a 3D object, so which we are going to project this onto a view plane, which is a 2D surface. And when I'm doing this, there is something called as front face, the back face, which is invisible. We call this as invisible face. When I'm talking about 3D viewing, I told you, so it is similar to 2D viewing operation. But what we need to bring in is how we are going to talk about the projection components when we talk about 3D viewing. Along with the projection, the next component was the visible surface. That is, what do you do with the visible face? What do you do with the non-visible face? That is what, if I want to take any operation, any action on what I'm going to do with the non-visible surface, first of all I should be able to detect which is the visible surface, which is a non-visible surface. Then later on I can think what I'm going to do with this. That is what now we're going to discuss about the visible surface detection method. Fine. So now when you talk about the visible and not visible, just look at this. I'm going to have a cube. Right now I have been displayed the cube where I am going to have two faces, the front face and the back face. So this is front face because this is overlapping some part of the other rectangle. Hence we say this as the front face and this as the back face. Now this is the center of projection or the view direction what I am viewing the object. And through this direction if I view, so this is going to be the front face and this is going to be the back face. And now if I am going to change the view, so right now I am going to have this as the front face still, and still this is the back face, but more part of the back face has been overlapped from the front face. And if I further move this projection, now you can just see, whatever the back face until now was visible, it's now not visible. Even part of the face is not visible. Hence this is where we call this as not visible face, and whatever is right now it's visible, we're going to call this as front face. And so now when I'm doing this, I should be clearly hold the information of the back face. Either is it visible, is it partly visible, or is it not visible. I should be clear with this. And that is where we're going to talk about the visible and the non-visible operation and the structure. I hope it's clear right now for you what is visible and not visible. And when I want to decide which is visible and not visible, and if I want to differentiate an object's face, the visible and not visible face, we're going to talk about visible surface detection algorithms, or even we can call this as hidden surface elimination algorithm. And before I'm talking about elimination, first you should be able to detect which is the face which is hidden or which is visible. Hence you can either call this as visible surface or hidden surface elimination algorithm. And now there are different types of algorithms what you can make use or what you can apply on an object to identify whether is it visible or not. And so now we talk about classification of visible surface detection algorithm. And so now whenever I am going to have the classification of visible detection algorithm, we are going to talk about two types. Fine. The first type is the object space methods. The next type is image space methods. I am going to have two types, object space method and as well as the image space method. This is the how we're going to classify the visible surface. If I want to say a surface is visible or not, I can distinguish these two surfaces either using the object space method or by using the image space method. Now we'll just see what is object space and what is image space. When I say object space, so the individual object I'm talking about. Individually, if I'm going to have two triangles there, I call triangle 1 as one object and triangle 2 as second object. Hence object wise I'm going to discuss when I'm going to be in object space methods. But when I talk about image space, all the objects in the scene is one image for me. Hence we call this as image space methods. Fine. And so now by having this, when I say object space method, so we compare our individual objects or part of the objects to decide which object is at the front or which object is at the back, and which is visible and which is not visible. If I talk about image space, so it compares point by point at each pixel position at the projection plane, because the entire scene is an image for me and I should compare point by point and pixel by pixel, so to come out with a conclusion which object or which part of the object or which surface is visible and not visible. So now we are just going to have these two methods or approaches what we can use, and the most visible surface algorithm use image space method, because it's easier to handle. Instead of identifying the object and later on working on the visible and not visible, image space method is easiest to do, hence most of visible surface algorithm use image space method. And we are going to perform this operation either in the object space or image space by using sorting and coherence method. Fine. We are going to sort the objects and we are going to exactly tell which object is in the front and which object is in the front along with the part of the objects too. Or we are going to use a coherence method. I'll just tell you what is sorting and how the coherence method is going to work with. Fine. So when I'm going to talk about sorting, it's just to use a facility where we're going to have the depth comparison along with the z value of each object, each surface. I can sort the objects and I can exactly tell which object is at the front and which object is going to be at the back. So depending upon this, we are going to decide which object surfaces should be visible and not visible. And so by sorting, we are going to have a ordering individual surface in a scene according to their distance with respect to center of projection. So from the center of projection or from the view plane, what is the distance of every surface in the scene of an object? Depending upon this, we are going to sort. When I say coherence, so we are going to take the advantage of regularities in the scene. So whatever the object we are going to have, we are going to compare the objects and its surfaces, and we will see what regularities we can fetch from this, and using this regularities we are going to decide so which object is going to be or which surface is going to be overlapped by the another object and so on. And so now whenever going to talk about the algorithms, the first easiest and simple algorithm is the backface detection algorithm, so which is going to depend upon the object space method, the first type of method, and this is going to perform the front back test. That is a point. If I take any point xyz, we call this as, or it is going to be behind a polygon surface. It can be part of the object, part of surface, or anything. For example, we are just taking a point. So we say a point is behind a polygon surface if this equation is going to be true for the point. I know what is the point. It is x, y, and z, and a, b, c, d is going to be the plane parameter for the polygon or the plane surfaces. Using this plane parameter on the surfaces, and if I'm able to derive this equation, whatever the value I'm going to get, if it is less than 0, then the point is behind the polygon surface and it is the back face. And if this equation fails, if the value is equal to 0, it is on the surface. I'm going to a polygon surface and the point is exactly on this surface. And if it is greater than 0, it is forward or it is front, and the polygon surface is behind this. So this is how we are going to decide or work out with the front back test of any point or a polygon or a part of polygon in your scene. And now by having these parameters, so for example, we are going to have a cube. And in this cube we are going to have normals. So every surface of your object is going to have its own normal values. If you remember the three parameter, the normal vector, the up vector, the direction vector, what we talked when talking about the 3D viewing in the previous session. So now when you're going to talk about any object, every surface of the object is going to have its normal vector. And now the view or the center of projection, wherever it's going to have, this is going to decide which surface will be visible and will not be visible. And now whichever the normal vector is going to be in the opposite direction of the view, so that surface will be not visible for the viewer. And whichever the surface normal value is visible or can be in the direction of the viewer, that surface can be visible, and that surface we call this as the front face. Whichever the normal vector is towards the viewer, we call this as a front face, and whichever the normal vector is going to be away from the viewer in the opposite direction, we call this as a back face. And so now when we are going to have a cube with normal value, we can decide what face is visible and not visible. Hence we say if face is in the opposite direction, then we are going to discard this. So depending on having a back face, this is going to be the back face. That is, how do we do this? As I told you, if the normal vector of a face is pointing in the direction of the center of projection, then it is front face, else it is a back face, and we can discard this. This is how we are going to have the back face detection. And just one more example to have a clear picture about this. Now we are going to have a camera, and if the vector what the camera will give us, we are going to call this as V view. And now this is the face which is going to have the normal vector. So this is going to be towards the camera, but you can see the normal vector of this face is going to be away from the camera. Hence, if I am going to multiply V view into n, if it is going to be greater than 0, then that surface should be visible. That is going to be visible. And if it is less than 0, that is not going to be visible. And this is how we are going to work with the vectors. If it's not with the equation, we are going to work with the vectors to identify which is the front face and which is going to be the back face. And if the z component is involved in the equation, then we are going to, if this z component is involved whenever we are going to talk about view operation, and if this c value is going to be less than or equal to 0, then we are going to say the face is the back face. And if c is not equal to 0 and if it is greater than 0, then we are going to say the face is partially visible or is going to be totally visible. Hence when we are going to talk about c, we are going to apply to this function. And now with this back buffer, we are going to have one more algorithm called as depth buffer method. And now this is an image space method algorithm. This depends, or this is going to fall into image space category. The previous back face detection algorithm or method is going to be part of object space method, and this depth buffer method is going to be part of image space method. And using this method will be applied to the scene containing only polygon surfaces in the part, which is going to compute the distance from the view plane along the z-axis. This is the view plane and this is the z-axis. We are going to compute the distance of the surface 1, the distance of the surface 2, the distance of the surface 3, depending upon the distance. So now we are going to compute whether the face or surface is going to be the near or the front or the back. Depth values, so which is going to range from 0 to 1. That is, if it is going to be near, it is going to be 0 if it is on the view plane, and if it is going to be far away on the far plane, it is going to be 1. Hence, so we are going to have the value, the depth value is going to range from 0 to 1, and whenever you want to implement the depth buffer, we need two buffers. One buffer which is going to act as color buffer, where we are going to load the colors, and the second buffer is going to contain the depth values which we are going to compute in the form of distance. Hence we are going to have two buffer. One buffer will hold the color and the other buffer is going to hold the depth values. Hence we are going to even call this as Z buffer method. The depth buffer method is also called as Z buffer method because the distance what we are going to compute, it is going to be on the Z axis. Hence we call this as Z buffer method. And this is the algorithm how this is going to exactly work. As I told you, now this is going to use two buffers, the depth buffer and the frame buffer or the color buffer. And this frame buffer or the color buffer is going to store the color. Right now this is going to store the background color at the initial state, and all the values of the depth buffer is going to be initialized to 1, so which will indicate every object is going to be on the far face right now at the initial state. Hence the first step is initialize the depth buffer and the frame buffer at all the points on your view plane, that is XY. Whatever the pixel position on the view plane is going to be, for all those pixel positions we need to initialize the depth buffer with 1 and the frame buffer with background color. This is the first step. Second step is we are going to process each polygon in a scene one at a time as follows. We'll take every surface of the scene from the polygon and we're going to compute such a way for each projected XY pixel position of a polygon. So calculate the depth Z if not already known. That is, we're going to compute what is the Z value. We'll take one surface, on that surface a pixel position. We're going to get what is the Z value of that. Once the Z value is obtained, we are going to compare that Z value with the depth buffer at that position. So from this projected position, we have picked the Z value. This is compared with the same position in the depth buffer value. If the Z value what right now have been picked up, if it is less than the depth buffer, we are going to update the depth buffer. We are going to update the depth buffer by saying set depth buffer x comma y equals z. Clear? Hence if the z value right now, if it is less than 1, then we need to update the depth buffer with the z value of the current surface whatever I have been picked. And at the same time for the position which the condition becomes true, I need to compute the surface color. Whatever the current surface color at the position XY is going to be, that color should be picked, and I need to set the frame buffer of the XY with the surface color whatever I have been just computed. Hence until this point the XY point was with the depth value as 1 and the color was background color. But due to this condition is true, I have been updated this with this XY point with the Z value, and this XY point I updated with the surface color. And I am going to perform this operation for every pixel of the object surface of every object. Every individual object surface we are going to pick out, and we are going to compute the depth buffer as well as the frame buffer. And this will exactly tell me what point at the end I am going to have the first surface. The Z value of this is going to be less than the far, that is 1. I have been updated this. If there's any other surface in front of this, then obviously the Z value of this surface should be less, and I'll be updating the depth buffer with this face. If in case I'm going to have any other face going to be behind this, and if I update the Z value of this surface, then I would have never updated with the second surface, because the Z value of this surface will usually be less than this surface itself or greater than this surface. Hence we are going to use this algorithm to decide which is going to be the back face and which is going to be the front face. Hence whichever the point is going to be at the back, so we are going to have this in the depth buffer, and whatever the color the surface is going to have, we're going to put as frame buffer. And once all the surface has been computed, after all surface has been processed, the depth buffer contains depth value for the visible surface. Frame buffer contains a corresponding color value for all those surfaces. And this is how we're going to sort. We're going to perform sorting operation or ordering operation of the surfaces and decide which surface is the front face and which is going to be the back face. This is how the depth buffer algorithm will be used in your program. And now we are going to have the equation, whatever we are going to have, that is the planar equation to decide the back face and the front face. We can use this equation whenever I want to compute the z value. It is not simply we pick the z value of that point. When I want to compute what is the z value in this algorithm, now we are going to use the same planar equation and we are going to rearrange this. When we rearrange, we are going to have z equals minus ax minus by minus d divided by c. The same equation we have been rearranged this. And if I want to find the newer, I'm going to have newer surface, the another surface. If I want to find new z value of that, I'm going to call this as z dash, and instead of x we are going to have x plus 1, and I'm going to have y and minus d. And if I want, I can make use of this as y plus 1 and talk about one more surface. Hence we are going to have this two operations. So I'm going to rearrange this and I'm going to say this as z dash equals z minus a divided by c. And now whatever the a divided by c, what I'm going to have, this is going to be which is the front face, which is going to be the back face. Now this is all about the visible surface and not visible surface. Thank you for this session.